All right. Hello, everyone. Welcome to the reading group. Today, I'm going to keep talking about Gaussian processes and determinantal point processes. So just from last time, we have covered like motivating examples of Gaussian processes, and then we discussed the difference between parametric models and non-parametric models. We also talk about the definition of Gaussian processes, how we can do inference and learning with Gaussian processes. So for today, I'm going to start with like 2 slides of review of what we have covered last time. And then after that, I'm going to introduce several different kernel functions, which we discussed last time, but I didn't give you the explicit formula for that. So I owe you this part. We will get there. After that, we're going to look at so-called deep kernel learning, which is a method try to combine the deep neural networks and the Gaussian processes together. After that, we're going to look at like one paper that I found. It's relevant to both Gaussian processes and graph representation learning. So it's like finally we see that the Gaussian process is not something like too far away. It actually connects to the ongoing research in our group. So this will finish all the discussion of Gaussian process. Then I will introduce the idea of determinantal point processes, which is define of distribution on sets. So Gaussian processes like define distribution on functions. These are like 2 different things, different from what we are so used to, like define distribution on just a single random variables. All right, with that, let me get started. So let's first see like the definition we discussed last time about Gaussian process. So a Gaussian process is a collection of random variables. You can imagine there are like infinitely many of them. So that's why we say it is actually a function. And then for all of these infinitely many variables, you can select finite number of them. Then we're saying for any collection of this finite number of random variables, they have a joint Gaussian distribution. In this case, the Gaussian distribution only needs like 2 parameters, the mean and the covariance. The mean can be determined by the x value of these random variables you selected, and the covariance can be determined by like a pair of x values that you selected. So this makes the Gaussian process a non-parametric model, because when we apply it on our own data set, the parameters, so meaning here the mu and the k, actually grows together with the number of samples we have in our data set. So if we collect more data here, we will have more parameters. So we call it non-parametric. We also talked about how to use Gaussian processes to do prediction. Like in this case, we saw this picture last time. So the Y2 contains 4 different points. These are the observed points. And the Y1 contains 3 different points that are the values we try to make predictions on. So it follows the formula like this. We have the joint distribution of Y1 and Y2, and then it is a Gaussian distribution with certain mean and covariance. Last time I didn't give this part, so I guess that caused some confusion. Here, if we explicitly write out what are the A, B, and C, they are actually the kernel functions applied on the x values. So for example, A is just the kernel function applied on the x1s, and then B is a kernel function applied on x1 and x2. So in this case, we know the covariance between Y1 and Y2 actually depends on like 2 things. One is the values of this axis. The other one is the parameters inside this kernel function K. If we have this ABC, then we can come up with this conditional distribution, Y1 conditional on Y2. So that is saying, given the observed Y2, we actually know the distribution of Y1. So it will be looks like this. So we can compute this new mean which is the prior mean we put on y1 plus this correction term. This correction term involves the covariance of y2 and the prior mean we put on. Well, this in this case is not prior mean, it's what we observed of y2. And then finally we see that this is a linear function of y2. So for the covariance, we can also see we have this kernel function applied on the x1s only contains information from y1, but we can also do this reduction in uncertainty because we have already observed some values close to y1, right? So then we are more certain about how the values of y1 should distribute. So the covariance actually gets smaller. So in this case, following these two formula, we're going to get a prediction of y1 and also the uncertainty of our prediction. This is like a short review of concepts we discussed last time. Next, I'm going to like get deeper into these kernel functions. As we already discussed last time, there could be different kernel functions serving different purpose. And then the most common one, and the one we have been seeing along the way, is this so-called exponentiated quadratic kernel. So I guess I guess we are more familiar with another names of this kernel, maybe like Gaussian kernel or RBF kernel. So it's all about the same thing. So basically, we're going to compute the distance between two inputs, xa and xb, and then we're going to use two parameters to control this kernel. So one of them is the sigma. In this case, represents the overall variance of this kernel. And then we also use this L to control the length scale to see like basically saying how far away of x1, xa and xb is considered far enough, right? So if we draw it out, it could be like this. When the L equals 1, sigma equals 1 is this blue curve showing in the plot. But if we reduce this L, make L smaller, that is saying for the axes are actually far away. I consider them as like uncorrelated. They are not. They do not have a big influence on each other. But if I increase the L, I'm saying I'm going to consider a longer length scale. So even though xa and xb are far enough from each other, I still consider they have like a slight influence on each other. Also, I can change another parameter sigma. So if I still start with L equals 1, sigma equals 1, but I reduce the sigma to be 0.5, in this case, I'm saying, well, in general, all of these points won't have a very big influence on each other. Their covariance won't be that high. So they are more independent. Yeah, I guess the idea of this Gaussian kernel is pretty intuitive. And then we can look at, in this case, when we actually draw samples specified by this Gaussian kernel, how the functions look like. I will make this a little bit bigger. So if we are following this Gaussian kernel with, I'm showing two different parameter settings, L equals 1, sigma equals 1 versus L equals 0.3 and sigma equals 1. So in this case, we're showing sort of this covariance matrix here. And then we're showing the functions we can draw out of these settings. We can see that for the Gaussian kernel, it is actually saying that points close to each other have a high influence on each other. Points far away are like not very related to each other. So the y values is like if two x are close, then the y values are also likely to be close. So this is like a smooth kernel we defined on our data. Compared to the Gaussian kernel, I guess I gave this periodic example last time, but I didn't tell you the specific form. So here is a very different case, very different kernel, where it involves these sine functions. Although we are also taking the difference between two input points, xa and xb, but we put it inside this sine function. So if we look at the kernel itself, it will be very different. In this case, even 2 points are like far away from each other, but they can still have high influence on each other. For example, this point here, right? So for example, if we look at xa minus xb equals -1, so they have this distance, right, -1, but still the kernel function gives us like covariance equals 1. So we can use 3 different hyperparameters to control this periodic kernel. The sigma square is similar as before, the L is similar as before, but we have one additional P to control like the period. Basically, we are saying that like for this kind of repeated curves, how much the repetition, how much the distance we want between different repetitions. So with these 3 parameters, we can actually get kernels looks like this. And then if we draw samples again from this kind of kernels, we're going to get curves looks like this one here. So first of all, notice the covariance matrix looks very different from before. Not just the diagonal, but all of this kind of off diagonal terms, we can still have very high covariance between them, right? And then if corresponding to this covariance matrix, we draw samples out of it, we can see the samples actually looks like this sine curves, or at least it follows this periodical distribution. If we slightly change the hyperparameter, in this case, if we make L larger, we still get the periodical functions, but they are like relatively smoother in this second example. Yeah, these are like 2 different examples of kernel functions. Actually, we can combine these kernel functions to get new kernel functions. In this case, I'm giving one example, so-called local periodic. So basically, it is a multiplication of the previous 2 kernels. So in total, we're going to have 4 parameters. And then we have a sigma parameter as before, and 2 different L's control the landscape of 2 kernels, and then P as the period. So in this case, if we combine both kernels, we're going to get something looks like this. So for the X close to each other, for XA and XB close to each other, for sure, they're going to have like high influence on each other. Their covariance is very, very high. And then for X and XA and XB far away from each other, the covariance is going to gradually reduce. But out of this pattern, we still see this periodic pattern as well. So we still see here is this looks like this sine function. So we can get the smoothness between points and the periodicity between points at the same time. So to see some function samples we can draw out of this new kernel, it looks like this. The covariance matrix is kind of a combination of both cases. On the diagonal, you have the highest value. For the other off diagonal terms, you still see some relatively high values. But if you get to very far away, like these 2 ranges, it's still like points are basically have no influence on each other. So if we look at the functions we draw will be both smooth and have this periodicity. So this is the kernel. And then I have one example of when this kind of kernel will be useful. So in this case, we consider this airline passenger prediction problem. So the data set is showing from 1950 until 1960, and then the number of passengers of airline. In this case, we see the general trend is growing. More and more people are choosing to travel in airline. But at the same time, we also see this periodic pattern, right? That's because for airline, it's like a seasonal thing. So maybe in the summer, people are more likely to travel. In the winter, people prefer to stay at where they are. So we actually want to fit a model to capture like both trends. In this case, the Gaussian process with the kernel we just talked about is a perfect choice, because we want the points to have a high influence with each other when they are close, like the 1960 and 1961, right? If we look at two axes here, the y values should be correlated. And also we want to capture this periodicity. So in this case, when we fit this, this is actually what we fit for our prediction. When we fit this, we can also get this periodicity. And then here, the shaded area is showing our confidence. Like it's a 95% confidence level, showing that how confident we are about our prediction. We can see that this is actually a very reasonable prediction. Yeah, so I guess we reviewed some parts that I feel like may cause some confusion last time. And then I give you like what I owe you, like examples of different Gaussian kernels. In reality, for which task or which data set you should use what kind of kernel, this is still like ongoing research. And then there are actually much more complicated kernels than these ones I just introduced. So I guess if you are interested, you can also look it up. But I can also take some questions right now if there are any. Okay, so seems like the confusions are cleared and we get more intuitive understanding of different kernels. Then let's actually go through the new topics of today. So we're going to discuss like one work of combining the deep neural network and Gaussian process. First of all, I want to point out that right now people are like very fascinated with deep neural network. Basically, for everything we say, okay, can we model it using a deep neural network? I guess one reason is because we have this universal approximation theorem saying that if you have a infinitely wide two-layer neural network with value activation, you can actually approximate any continuous function in a compact space. In reality, there is a similar statement for Gaussian process. It is saying that if you define a Gaussian process with certain kernels, then you can also approximate any continuous function in a compact space. To me, I recently did some reading about universal approximation theorem. I feel like it is actually a bit far from the reality, because although we have this theoretical guarantee that we can approximate any functions, but when we actually apply deep neural network or apply Gaussian process, there are so many other tricky things like optimization or like how do we actually search out of the optimal solution, like different things we need to worry about to actually find that approximation. So in reality, people actually try to use different models, or in this case, combine Gaussian process and deep neural network to bring the best of these two models together. So this is what this work by Andrew Wilson is doing. The idea is actually very, very simple. So they have a like deep neural network, and then they just train this deep neural network with whatever data they have. After that, they will take the final layer representation and plug it into a Gaussian process. And then in the paper, they show that if they do everything like this, then it is equivalent to, well, somehow equivalent to having an infinite dimensional layer as their final layer. So it's like before the neural network stops here, and then they directly use this for regression or classification. Right now, because they plug in the representation from this layer into a Gaussian process, they say the new model is kind of like a neural network with this architecture. And then when they actually do the training, they first do the neural network training. And then once they plug in the neural network representation into Gaussian process, they do the joint training. So in the second phase, they also tune the parameters inside the neural network. So that's basically the idea. And then they claim in this case, we can combine the inductive bias of deep models, and then we can also get advantage of the non-parametric flexibility of Gaussian processes. And additionally, because Gaussian process is like a Bayesian model, we can also come up with the uncertainty estimate, so which could be another advantage. So in this case,
Shichang, yeah, that's a very interesting. I don't know whether you're going to elaborate it or not. Is this one slide, or you're going to elaborate this idea more in future slides? Because I do have questions.
Okay, so the next slide, we're just going to talk about we can have different base kernels. But if you have questions, I guess we can discuss it right now.
So I just want to discuss the connection to this variational deep learning model, because it seems to me it's like instead of directly utilize the final output layer, right, and then fit it into downstream task, so somehow they want to add a prior to it. In other words, we're going to treat that all those things are sampled, so which means that they are random variables, right? So do you think this is essentially one special case of these variational models? Okay, so probably I can say more about the version models I'm talking about. So in the simple case, right, so we can just say that, okay, at some stage, the representation is sampled from, let's say, Gaussian distribution. Then we're going to generate some like parameters, right, based on what we have observed, let's say the mean and the standard deviation of a Gaussian distribution. And based on that, we can sample from that distribution. Then we can, just get those representations. But definitely those are kind of, it's no longer deterministic. I just wonder, like, but according to just I described, I think there's still some difference in the sense that in the variational model I described, we are going to use neural network to generate the parameter in a deterministic way, and then we're going to sample kind of latent representation from that distribution. But in this case, it seems to me the prior is given. Right? I mean, the Gaussian kernel prior is given.
Yeah, so let me try to answer this question, and then we will see whether we need more discussion. So I guess from what you just described is that we have some like data sets with X and Y's. We use neural network to maybe like learn parameters of this distribution of our data set. As you pointed out, we assume Gaussian distribution, so we can learn the mean and the covariance. In this case, it's like for each, so for the X, we're actually learning this final layer representation. And then for the Gaussian process model, this final layer representation is kind of like the parameters inside the Gaussian process. Because for Gaussian process, like all the observed data can be think of as the parameters of our model. So in this sense, I guess these two are the same thing. But if we're actually talking about the parameters for Gaussian process, the actual parameters are like the hyperparameters. For example, the sigmas and the L's we saw before, like control the length scale of the kernel function. So for those parameters, we need to explicitly learn them. So yeah, I guess this is my answer.
Right. So, okay, then I think the difference is like in the previous case, for example, if we just assume they as like regular Gaussian distribution, then the parameters, it's like it's still kind of parametric model, right? So that's why you have just you only need to have a few parameters to be learned, and then you can sample like representation from that distribution. But here, since it's like a non-parametric model, so it's like the highlighted portion that you use red color is secured that last layer, right? I think instead of considering them as parameters, then it's just okay. Well, based on those data points, we try to compute the kernel, right?
Yeah.
Okay.
Yeah.
Mm.
So yeah, I think this is for non-parametric models. Sometimes the terminology can be a bit confusing because
But then afterwards, still, if we okay, of course, a non-parametric version can be considered. Okay, we have like infinite number of dimensions. But then after that, actually, the idea is quite similar. Essentially, we assume the later part is going to be sampled from that Gaussian distribution. I mean, Gaussian process. Well, the kernel is determined by the last layer.
Right. Yeah. Okay. In that sense, it's very similar. Yeah.
Then from inference perspective, like in the traditional like a version model, people use versional inference. And here I just wonder like technique wise, how do we solve this inference problem? Or is it still similar?
So for the inference, it's also like this picture right here. So once we get like more data we want to make prediction on, we just assume a joint distribution because everything is Gaussian, right? So here we assume that everything is always joint Gaussian. For Gaussian, we don't need come up with this reference distribution like in variational inference. We can always make like analytic forms of our predict. We can always write down the analytic form, and then in this case, the prediction we want to make are just this y1s where we observe the corresponding x, but we don't know the y. So we use this conditional distribution to make prediction.
I have even more primitive question, actually, a lot of primitive question.
Yeah, oh, of course. Yeah, go ahead.
I first, before you even go to the deep neural network, let's first think about the problem of obtaining hyperparameters of a particular Gaussian kernel given a data set. So now what we are trying to do is that we have already determined on a particular form of Gaussian kernel and the covariance kernel, what I mean, covariance kernels and the shapes of the covariance kernel. Yeah, covariance kernel. And what we want to figure out is I want to figure out and we have a lot of past observations on a particular domain regarding the coordinates of the function and the value of that function. You have a lot of those past observations. Now, given that, what I want to figure out is I want to figure out what is the hyperparameter that I can use so that in the future I can use that hyperparameters to predict unobserved variable given the observed variables. That's what I want to do. So how do you do that?
Yeah, I guess in the case you just described, it's like I haven't have any y1s yet, right? It's just I defined a Gaussian kernel, and then I observed like several y2 points in this case, and then I want to use these y2 points to determine my hyperparameters, like the L, like in this case the sigma and the L.
No, that's not what I want. I already have observed everything.
You also observed the y1.
We observed y1, we observed y2, we observed all those. What I want to do is because now I have determined on my Gaussian kernel, the covariance kernel, I want to figure out what are the parameters of L's, the parameters of sigma, or the parameters of P that I can use so that once I settle on that parameter, I can use it so that in the future, when I have a partial observations of y2 and not y1, then by combining that partial observation with the hyperparameters of a given covariance kernel to predict the y1 value. That's what I want to do.
So in this case, if we are saying like, okay, so for this y1, it actually refers to like the x values of y1. How do I write this? Maybe like the x value of y1 and the y value of y1, right? So in this case, we don't know this part, right? So for selection, the
No.
sigma
So that I
squared
don't care
else,
for now. I don't care for now. All I want is I know all this. And now I want to estimate the hyperparameters, P's, L's, and sigma. How do I do that?
you just maximize the Gaussian likelihood, right?
So how do you do that?
So yeah, so okay, I guess we need to be clear about what is y1 and what is y2 in this case. For y2, you fully observe its x value and y value, right? For y1, like all the blue things showing in this slide, it's something you observe the x, but you still don't know the y. And then because you don't know the y, you cannot like directly use it to compute the likelihood. So you can just based on the y2 to compute the likelihood. When you only use y2 to compute the likelihood, in this case, you're going to need a C, right? You're going to need its covariance. And the C involves this kernel function, involves those parameters, hyperparameters we want to estimate. So if we can maximize that likelihood, we can choose the hyperparameters of this Gaussian kernel. And then after that, if I have some new values that I only know x, but I don't know y, right? So in this case, we denote it as y1. So these are the ones I only know x. I can use those hyperparameters and to make predictions.
But it is not that I have only one set of y2s. I have multiple sets of y2s.
What do you mean by multiple sets of y2s?
I observed one set of y2 for a particular function, and I observed another set of y2s from another particular function. I observed another set of y2s for another particular function. But I know that these functions, the covariance structure between the y values of these functions are all under the same Gaussian process. So here, what I want is now, given that I want to figure out what's the hyperparameter of my Gaussian, the covariance kernel, that's what I'm trying to figure out.
Yeah, if that is the case, you can just put your multiple y2s together, like concatenate them together as a longer function, as a longer vector, and then figure out the covariance, like the bigger covariance matrix.
I doubt that it will actually work.
Why is that?
Because these are different functions. It's just that the functions share the same covariance structure. So when I put them together, so y2 covariances on one function will be very different from y2 covariances from another function. Because it's just that these functions are sampled from the same Gaussian process. And what I'm kind of not sure about is that we can just multiply them together, multiply the likelihood together. But what I'm not sure about is that if I have different number of point samples for each of these functions, then how do I take that into account? Because some Gaussian covariance, some functions I have more data, some functions I have less data. So would it affect or would it not affect? I'm not sure. That is the part that I'm not 100% sure.
So I think here what we are saying is that for all different y's, right? And then we assume, like as you said, we have multiple sets, but we assume when we put them together, all of them follow a Gaussian distribution. So if let's say we have okay, we have too many y's. Let's use y21 and y22. Suppose like this is, as you said, like two sets of y2. And then each of them will have their own covariance captured by this part in a Gaussian distribution. I'm writing out the covariance function here. But if they are different, their own difference will be like captured by their own part of this covariance matrix. And the interdependency between Y21 and Y22 will be captured by these two parts. So we just assume jointly they are a Gaussian, but they could have very different covariance from this part to this part.
Well, I completely disagree with your statement, actually. I don't
like
think
which part?
Well, the fact that we put them together into a single matrix, I don't think so. No, I completely disagree. But anyway, so that's fine. So then let's move on. Let's put that aside. So the next one is, can you go to the next slide?
Yeah. This one?
Next slide, the deep Gaussian kernel thing.
Deep Gaussian kernel?
Yeah, deep neural network structure.
This one?
Yes, that one. So there, I'm not clear about that blue layer, exactly what it does. So what does it mean that we put that as the Gaussian? So that blue layer is supposed to be a Gaussian kernel, Gaussian process layer, right?
Yeah.
What are the H's there?
Oh, so let me draw a different diagram here. So we have input X, we have a neural network like this. I need a bigger space. So we have X, we have input neural network, we have H, and we use this to do whatever prediction we need to make for Y. This is a standard neural network layer, right?
Yeah.
And then for the Gaussian process, what we do here is that we take this H, we plug it into a Gaussian process, and then we use it to make prediction for Y. And then this diagram on the right is saying that if we do this, if we follow the second path I just draw, it's equivalent as plug in one final layer after this H, and then this final layer will contain infinitely many neurons. That's the claim in the paper.
Yeah, I think I can comment.
Yeah.
So I think there's a theory says that for the Gaussian kernel, actually it's, if you look at because like kernel, right? So essentially we can think about, we have this magic function that map the input to some other space, and then in that space, then we can carry on this inner product, and then that's the kernel. So if the kernel is Gaussian kernel, then actually the mapping function is mapping from this input dimension, well, maybe one dimension to this infinite dimension. So I think that's the meaning of H1 up to H infinite here. And so, for example, if it's just a polynomial kernel, right? So we know that essentially we just use the polynomial transformation. Then from X we can get that those polynomial terms, and then we do the inner product. But then it's just 1 plus X to the power of H. But if we wish to have this Gaussian kernel, then we have to do this infinite dimension of mapping.
Yeah, I guess, thank you for the comment. What we're discussing here is more like we have two input X1 and X2. Once I go through the neural network, I get both of their representations, H1 and H2. If I plug H1 and H2 into a Gaussian process and figure out their the inner product under the kernel, it's like I first do this infinite layer transformation of H1 and the infinite layer transformation of H2, and then do the product of their the transferred result. So that's why we're saying it's equivalent to have this infinite layer at the very end.
I still don't understand what it means that you feed H1 to Gaussian process and get Y. What does it mean?
Oh, it's like So still it's like when we do prediction, right? So suppose we have x1 to xn in our data set, and then we want to make prediction for xn plus 1, right? This is the train, and this is the test. So what we're going to do is that we're going to plug in all of h1 to hn and h2 into the Gaussian process, and then we're going to compute the covariance between them. Finally, we want to find out this conditional distribution of yn plus 1 giving h1 to hn and y1 to yn and hn plus 1. This is like we have n training data and 1 data we want to make prediction.
What is hn plus 1?
And then what is hn plus 1? Is when we plug in xn plus 1 to the neural network, we get its representation hn plus 1.
What is xn plus 1?
It's the point we want to make prediction on, like your test point.
And how does that affect, how does the y1 through yn somehow affects the yn plus 1? Is it a sequential data?
No.
Then why do you have to, why is yn plus 1 somehow dependent on h1 through hn? Shouldn't it be just dependent on just hn plus 1 or xn plus 1?
So once we model everything as a joint Gaussian, this sort of becomes the parameters in our model. The dependency
everything meaning that somehow we assume some kind of a correlation or covariance structure between different instances of our data set?
Yeah, right.
Yeah,
I don't think so. No, I don't think.
I think Shichang probably can go to the slide when you show prior and posterior. Probably that can explain. So I think right now, suppose we have like y1 up to yn plus 1 data points, and then they are sampled from this Gaussian process. So once we know the value of y1 up to yn, actually the order does not really matter. It's just like we know n values, and then we can write down the posterior distribution of like yn plus 1 given the observations that given the Gaussian process prior. And then that is just another like a Gaussian distribution. So that's why we can write down the likelihood to observe this one. And also we can, it's just a posterior distribution. So we can also estimate, for example, the mean of it and the variance of it. Yeah. So Shichang, do you want to go to the slide where the posterior?
Actually, I'm not quite sure which slide. Are you talking about the slide from last time?
No, it just reviewed it and in one slide. Yeah, this one.
This one?
Yeah, so you see,
okay.
Yeah, figure B is the posterior. So once we know something, which are the places that you have this kind of narrow, no shaded area. So those points, actually, you do observe them, right? So for any other X, the corresponding Y actually, just the kind of posterior.
I don't think this is really. Here, I think the fundamental assumption that we make regarding any deep neural network training or any machine learning problem right now is independence between two different instances of data. And what you're describing is essentially breaking that assumption. And I don't think that is the case, actually. We don't assume it. I think the correlation relationship is the correlation between the hidden layer HIs, not the HIs from the different instances of input data, but the different hidden layer neurons of HIs and the final observation, final prediction variables of yi. If we make that as a correlated variables and then apply the Gaussian process assumption, I think that does make sense.
So do you think this graphical model help? So here is like if we only look at x, they are just like the inputs. But once we plug them into Gaussian process, and then this f, this bar here is like a fully connected actually between different
indeed,
f's. Then the dependency comes from there.
Right, John, as you point out, indeed, in this model, then they assume that every data point is correlated with each other. And this correlation somehow is described by like how far away those two input x are. So the idea that if the input are close to each other, then the output y is also going to be close to each other.
Shichang, could you go to the slide that I asked you to show earlier, the deep neural network, kind of the one layer of the Gaussian process?
This one?
Oh yeah, that one.
Yeah.
I thought let me make sure that this is actually what you think. Maybe this is what Ijo thinks as well. Here is it. So I thought after hearing your explanation, I thought the assumptions are here. We see on the rightmost side we have y1 through yp, right? On the rightmost side we have y1 through yp.
Yeah.
Then one layer before it we have H1L all the way through HCL, right?
Yeah.
And I thought those are individual neurons at that layer. So then we can think about H1 through HC values as the Y. So in terms of what we talked about earlier, in terms of the Gaussian process model, we can think about those H1 through HC value as Y2 values that we have. And we can think about Y1 through YP values as Y1 values that we try to predict. The red one and blue one that you showed us earlier, if you model it that way, I think we can apply. Seems very natural to me, and also it makes sense to me that we can model it as a Gaussian process. But I don't know whether we have been saying the same thing or we have been saying completely different things.
I think we are saying like different things. Because here, like, okay, maybe this caused the confusion, but this is one single data point going through the neural network and making prediction, right? Yeah, yeah. So for the previous Y1 and Y2, that is like we're showing multiple data instances, like they jointly form a Gaussian. So each like Y1 or Y2 we previously show corresponding to one of this. So we had 4 Y2 and 3 Y1. In this case, in this kind of like diagram, we should have 7 in total X and 7 total Ys.
So let's think about. Go ahead.
Why do you have 7? Where is this 7 number coming from?
Oh, yeah. I'm just saying in the previous diagram we had like 4 Y2 and 3 Y1. So in total we have 7 data points. Yeah.
Oh, okay.
Yeah. So sorry about that. Yeah.
And here, why does it translate into 7 here?
Because we need to plug in all of this, right, into the Gaussian process. Or
to do what?
So maybe we look at only one. We look at only this point. So for this point, it's like we know it's X value. This is what we know, say X1, but we don't know its Y value. So what we will do is that we will compute this value, this conditional probability and then use it as like a prediction of its y value. And then for this conditional probability, we're going to use the information of these 4 red points we have already observed.
So Shichang, can you give us like application setting? So for example, are we doing like a time series prediction, which includes both the interpretation and interpretation?
That is a great good way to think of it. Yes.
Right. So maybe like just take this airline prediction example. So we have so here, because our training data is up to 1960s. So in the right diagram, it's like let's say like before this line, all the data are observed, right? And then for new data, say 1961, maybe we don't know what its corresponding value is, and then we want to find out. So we're going to consider this 1961 together with some points we already observed, maybe on this part. They form a joint Gaussian distribution, like these points, right? And then
so for all those years, including the historic data and the point that we're going to predict, all those will be considered as the X in the deep learning model?
Yeah, they will all be considered as X.
And for the Y, like a majority portion of them will already observe the value and want to predict the 1961.
Yeah, for the Y's are like Y's of these points, but not Y of this point. This 1961, not Y of this 1961.
So you mean the Y part is just the unknown part? We do not need to.
Yeah.
Okay, I see.
Yeah. And then in this case, this Y value of this 1961 will depend on the X and the Y values of these blue points, these green points, right?
Yeah. And so the loss function is determined like because the Y1 up to YP is another like Gaussian distribution, right? We just compute the likelihood under that joint Gaussian distribution. What's the likelihood to observe the observed or ground truth Y? Is that how we form our loss function?
So if we are talking about learning for the Gaussian process, like non-parametric model.
Right, but we have W. We have W in the neural network.
Oh, so yeah. Maybe let me decouple things a little bit. So if we don't talk about anything about neural network, the learning part is only learning the hyperparameters in the Gaussian process, right? And then in that part, so we can use like these green points as maximum likelihood to choose the sigma or the L of the kernel. If we're talking about the deep, like with the neural network, and then it will be like a 2-stage. So according to the paper, they first singly use the neural network to make predictions for this model and for this task, and then they tune the parameters. After that, they will take the final layer representation together with the Gaussian process, and then use it like a 2-stage model to tune all the parameters inside the neural network again. And then the loss function is maximize the Gaussian likelihood. Yeah. Yeah, regarding this deep kernel learning, anything else we need to discuss? Yeah, I really hope we can make this clear. Actually,
it's still not clear to me. Very confusing. Very confusing. I'm not sure exactly what you are doing.
Okay.
So here, the examples that you showed regarding the time series data is a one-dimensional function. So that one, I guess. But this is not a one-dimensional function. If you're kind of trying to say that here we are trying to model these H's and Y's as one input point and one output point of this overall thing. It's not one dimensional function. So in that case, how do we define the covariance kernel? Is it based on the distance between them, or is it?
Oh, you mean the choice of the kernel? So even if it's multi-dimensional, let me see whether I have that in my, yeah, okay, good. I have one example of the 2D case, right? If it's 2D case, the kernel function can be something like this. We just have like two L parameters, and then each of them corresponding to one dimension of the input X, and then we will see that we won't get like a one-dimensional function anymore. We'll get this two-dimensional curve.
And then in this case, so then do we also model the means as well?
Yeah, we also model the means.
I see. So that is another way. Another way to think about it. I see. So that is. Oh, I think that one also, that way does make sense too. So here, can you show me the slide of the deep neural network again then?
Okay. This one?
Yeah, so let's assume that, so here then we can think about, let's forget about YPs, right? So there is only one Y that we are trying to predict, because once you know the how to one, then the other ones we can just extend it, right? Replicate similar things, right? So we have one Y1 that we want to predict. Now we can think about this Y1 that we are trying to predict as a function that is defined on the domain of C dimensions, where the dimension coordinate values are given by H1 through HC. So that is the function that we try to predict.
Yeah, okay, yeah.
And then for every possible point in that C dimensional space, we have to predict the mean Y1, and also we have to predict the mean Y value, and we also have to predict the Y value correlations or covariances for different points in that C dimensional space.
Yeah, exactly.
So then what do we do? Different input data set will be mapped into different points in that C dimensional space. And then for each of them, we have their Y values as a training data set. And we can put them through the Gaussian process hyperparameter estimation process to figure out what those hyperparameters are. And once you get those hyperparameters, then we can use it in order to predict any future points. I guess we can do that.
Exactly.
Okay. So I think I get it.
A related question. So here, using the airline example, right? So we only have one time series, and you say that, okay, for the input layer, we're going to utilize all the timestamps that we are interested in to form this input layer. Then we just get just one data point, because the whole time series is kind of one data point. So then in order to train the network, do we need to have multiple time series?
Why it is a single data point?
Because here we treat all the timestamps, right, starting from 1980s to 1960s, right? So those will be considered as the X. That's the X1 up to XD.
So in this case, we actually have a like one-dimensional X and a one-dimensional Y. Maybe it's like a 1950. Sorry. Maybe it's like 1950, we have one X and one Y, 1952, 1954. So this corresponds to 3 points. But in reality, it's not this crude. So we may have more points. So we can get this periodic pattern. It's not a single data point.
Okay, so now I'm confused. Okay, I thought when we try to form that
Okay.
Gaussian process, we really need to observe multiple wise. Let me see how I can formalize. In order to really estimate that Gaussian process, we somehow really need to kind of define the kernel, right? So if we only has this one x value there, I don't think there's any way that we can really define that kernel. So we have to have many kind of potential x, then based on that, we can somehow define that kernel.
Right, we have many x, right? So I'm saying
even the input is one-dimensional, and then afterwards, but how we can capture the relation between that x and other x?
It's like we have this kernel function. So whenever we have a pair of axes, we can plug these two axes into the kernel function to figure out the covariance between the two corresponding y's. So is your question about the dimensionality of x, or
I think my question is like, what is the D and the P in that next architecture? Previous, I thought that D is just the total number of x that we have observed in this data set. So let's say.
Oh, you mean in this picture?
Right. So I thought that D.
This D is the dimension of the input. So because for neural network, each time we plug in one data point, right? Yeah. Sorry, this part can easily cause confusion. So this is one single data point. In the time series example, D equals 1. So this like a D dimension of a single point, and then P also equals 1 in the time series example.
Okay.
Yeah. So I guess the picture here is trying to be general to say, well, we can have multi-dimensional input and output. But for the one-dimensional function examples, the time series examples, D and P both equal to 1.
Okay, then I will think about it.
Yeah. Okay. Back to Zhang. To me, like what you just stated, right? The whole process. I feel like what you stated is exactly what I try to tell here. So I think you get it. If you have other questions, yeah, we can also talk about them, or you can stop me and ask anytime. All right. Then maybe let's continue. So, okay. So this page is just saying to combine these two things, the Gaussian process and the deep neural network, we can choose different kernels, like the periodical one and the regular one, like the Gaussian one as before, to control this. And then after that, we are going to look at like one example I found, like one paper I read recently, which applies the Gaussian process on graph data. Okay, can everyone still hear me?
Yeah, I can hear you.
Okay, good. So yeah, this paper is actually stuff I added before, like Professor Eric Xing didn't go over this paper. So, but I thought this is helpful, relevant to our group. So the statement is like the following: So given a graph G, and then given the corresponding features, like d-dimensional for each node, what we want to do is that we want to use a Gaussian process model to do graph level prediction. So it's like we want to figure out this function f that takes in the graph level information, and then you can think of it as the regression problem. You want to output a R. In this case, if we simply set up f like this is actually only the graph feature. So a function, a naive function like this is kind of like operating on the node features, but ignore the graph structures. So this is the problem what this paper is dealing with. I think the idea is actually pretty intuitive. For this paper, what they try to say is that, well, I have a function maps an input graph to a real number. So I want to break this function into 2 stages. So first of all, I will transfer everything from this node level feature to some other node level feature together with the sort of the interactions or correlations between different nodes. After that, I'm going to, based on this transformed feature, to do my final prediction. So this is like the setting of this paper. If we visualize everything, it's like before I only have this node feature corresponding to this phi matrix here, cardinality of V times D. It's a node feature. But then I want to come up with like different ways to capture the correlation between nodes. And then I will come up with this U matrix. And then for each set of hyperparameters, so here, J and K describes how many hyperparameters you have. So we think of this U as like a function. You can think of it as a kernel function, actually. So it depends on 2 different hyperparameters. The first hyperparameter has J possibilities. The second one has K possibilities. So by choosing different hyperparameters, you can produce J by K many U matrix. And each matrix is absolute V by absolute V, captures the interaction between a pair of nodes within your graph. And then once we got this different matrices U and the original node feature, we can just do a matrix multiplication. So in this case, it is showing taking 1 row of 1 U multiplied by 1 column of phi, then gives us 1 entry of this Z. Or you can think of it as like 1 U, like the first slide here, multiply this whole phi matrix, and then it will give you like 1 slice, like this slice of your final Z. And then I can take the second slice of U and then get this part. So in this case, it's like we manually defined some U function that allows us to capture the interaction between nodes. And then using that together with the original node feature phi, and then we get this this Z representation of each node, which contains both node feature information and graph structure information. So from there, we can define our F, the Gaussian process on this Z, and then it will be a standard Gaussian process because it's like each row here is the input X, and each Y is a corresponding real value we want to regression, right?
What is that J and K?
Yeah. So thank you for this transaction. I'm about to mention this. So J and K are actually just something like at a very high level. It depends on what kind of U function you use. So in the paper, they give 2 examples of these U functions. So the first one is that if the data you want to apply on is a manifold, then you can define your U function like this. It will contain 2 parameters. one corresponding to J, one corresponding to K. In this case, this function takes in 2x and measures the radial distance between them and the angular distance between them. So combine these two different distances, you will get like a weighted distance between x and x prime. Then one set of J and K gives you one certain distance. If you change the hyperparameters, you get another slice of U. So this is for the manifold. If we want to use it for general graphs.
Sorry, but I am quite.
Yeah, go ahead.
So somehow I think you want to connect this J and K to this radius and the kind of the angular distance. But yeah, what does that mean, right? So
yeah, so maybe we can look at this formula. So first of all, in the paper, it's saying that we can actually use any U we like. It's like the choice of kernel functions for Gaussian process. For different purpose, we can choose different U. They give this example because this example is a good U function that can apply on manifold.
It seems to me it follows the same family, but the J and K define some sort of hyperparameter, for some rho.
Yeah,
theta J.
J and K just define. So imagine for J equals 1 to big J, we will have theta 1 according to theta J. Then this part will change, right? So you will technically get a different U function.
Okay, it's kind of filters, right? So we're going to have J times
right
K filters
exactly.
to different types of kernels. Okay.
Yeah. So in this case, they call it graph convolutional, but it's not like the graph convolution we used to see in the GCN models. So like they explicitly define different filters. In this case, J by K different filters, and then they want these filters to capture the relationship between different nodes. And for graph data, they give another example of the U function you can choose. In this case, we are only left with one hyperparameter we need to choose. So the K is gone. It's only J. In this case, they are saying that it's like a Gaussian, right? But for the coordinates, we're considering kind of the inverse of the degree for two input points. We use the inverse degree of them as the coordinates, and then we will choose the hyperparameter rho to figure out the U function of x and x prime. And then we can definitely have other choices of the U functions, depends on what kind of data we're looking at. Okay, so this is the idea of this paper. Once we get this Z, it's standard Gaussian process. So I hope it is clear. And then some example data sets they considered, including this MNIST super pixel data set, which is we take the famous MNIST data set, convert it to a graph with 75 nodes, and then try to recognize the digit from this graph. The other one is 3D mesh, like the subject recognition. It's like they have 10 different people, and then each people, they record 10 different poses. And then totally they have 100 data sets. Then you will see like some like mesh, say 70 out of this 100 different mesh. And then for the other 30, they want you to predict like which person this is. So this kind of mesh classification prediction. And then in this case, if we use enough vertices, say 2,500, their model actually give quite good result with a very low error rate. Okay, so yeah, finally, I guess, finish the Gaussian process. Just to summarize a little bit, Gaussian process is a Bayesian non-parametric model that we can use it to represent distributions over smooth functions. Also, because we assume the Gaussian likelihood, so all the inference part can be done analytically and we don't need like sampling estimation, or we don't need like a variational inference. Finally, we see one example of combining Gaussian process with like deep neural networks. Sort of use the result of deep neural networks as like part of the kernel function. So yeah, the next topic we won't go very deep into because it's not used that often as Gaussian process. Gaussian process is still used very often. Actually, for iClear 2021, I saw like one paper also related to Gaussian process, and then try to do things like this, like mesh classification tasks. For DPP, it's used less often, but I think the idea is pretty elegant, so we can also talk about it. From the name, we can see determinantal, right? So it is related to matrix determinant. So let's see what it is. The problem we are trying to solve with DPP is about subset selection problem. Some examples include, I have a document, I want to select a subset of sentences to summarize it. Or I have a data set with very high dimensional features. I want to only select a subset of features. Or like I'm making product recommendations. I want to recommend out of many products, I want to recommend a subset to my user. These are the situations where subset selection is useful. And then sometimes we may have some requirements about subset selection. For example, we want the subset to be diverse. Take the 3 examples we just gave. We don't want like a summarization of a document. It's just repeating similar sentences again and again. We want the sentences somehow to be diverse. And then for the feature selection, still, we want the features to represent different perspectives of our input data, not just the very high correlated features. For recommendation as well, we don't want to make redundant recommendation. So with this diverse requirement, we have the so-called determinantal point process. So the determinantal point process is a distribution defined over subsets. We can think about it like this. If we have a whole set omega, and then we consider its power set 2 to the omega, then for every subset inside this power set 2 to the omega, we will have a probability associated with this subset. And the DPP is helping us to figure out what is the correct probability we should assign to each element inside this power set. So this is the problem we try to solve. And then the way we do it is that we will assign this probability to these elements with the diverse constraint. So saying we have a set of k items, and then we have a representation of each item. Then we will first calculate the gram matrix, basically represents the similarity between different items, L. So the ij's entry sort of tells you the similarity between item I and j. Then the probability we will assign to a particular subset is just we take the determinant of that subset from the matrix, divided by the determinant of this whole matrix plus I. I guess this will become much clearer if we look at one example. In this case, the gram matrix is a 4x4 matrix, represents 4 items in our whole set. If I want to select item 2 and 3, I will select it with probability equals to this, which is the determinant of the red part divided by determinant of L plus I. Everything clear so far? Okay, I hope everything is clear so far. Then let's get some like intuition behind this DPP. Why do we want to design it like this? So first of all, when we talk about the intuition, we can ignore this denominator for a moment, because this denominator is just a normalization term to make sure everything is probability. So we only look at the numerator, this determinant of the subset. So if we look at the determinant of the subset, what it is saying, right? So the determinant of this subset actually tells you the volume of the parallelly piped, yeah, a very long word, but basically this geometry. It tells you the volume of this geometry formed by the vectors inside your subset. If we consider like all the items you select are very, very similar to each other, and then they all pointing to like very similar directions, then your total volume will be very small. But in this case, if we want to like maximize the diversity, we want to select the ones that are different from each other. We want our subset to capture different perspectives of the whole set. Then for the subset with very different items, we will assign it a higher probability because the determinant will be bigger. So as I said before, in this case, we will use the determinant as sort of the probability, but we still need to normalize it, right? So that's why we have this denominator determinant of L plus I. In this case, I guess we won't have time to go over all the proofs of why this is the right partition function, because the proof is quite long. I have it in the appendix of my slide. If you are curious, you can read it. But basically, we will, the proof goes like, we first prove the following theorem, the theorem 1, which says whenever we pick a subset A of the whole set, then if we do a summation over all the determinant with the subselection contains this A, then this summation will equal to this value. Then the case we just talked about is the special case of the theorem where A equals the empty set. So it's like when A equals empty set, we are saying, well, for all subsets contains empty set, which is trivially just all subsets. If we sum them together, I will get the determinant of L plus I of subscript A bar. Because A is the subset, the A complement is the whole set. So this is the regular identity matrix. Then we get what we want. We get the normalizing factor. And then, so yeah, we have covered like the intuition and the simple setup of DPP. So there are some like improvements we can make over the simple setting of DPP. For example, we can consider a kernel version of DPP. When we consider the gram matrix of DPP, the simple version is just take the inner product or in like the dot product of the two input representations. But this can be easily extended to like a kernel function. Like whatever kernel function we like, we can use that to define the corresponding entry in our gram matrix. So we can get a different L. From this different L, like just following the whole setup, we get the kernelized version of DPP. Similarly, another kind of augmentation we can add to the regular DPP is applying neural networks on it. Like before, we don't use the raw representation of our item. Rather, we plug everything inside the neural network to get a new representation based on the neural network. And then we construct the gram matrix. We follow whatever we did before. And then when we want to make inference of whatever, like basic DPP, kernelized DPP, or neural network-based DPP, the inference we do is that we want kind of the best subset. The best subset in this case is that the subset selection that maximize my log determinant. But people have shown that this kind of subset selection the exact solution is an NP-hard problem. So we need to do some approximations. So imagine like for each item in your whole set, select it or not can be a binary variable of 0 or 1. If I don't directly treat it as a binary variable, but I just consider its probability, like between 0 and 1, I have done a continuous relaxation of my optimization problem. In this case, if I relax my selection variable to be value between 0 and 1, and then I relax my log determinant to be this slightly changed form, I can solve it, solve the optimization problem, and then round it back to the 0 and 1 for my best subset selection. So because we are finding the subset with the highest probability is actually finding the mood of the DPP. So that's the inference part. For the learning part, it's like what we discussed in the Gaussian process. The parameters we have are actually the parameters inside the kernel function. Like for the setup, the determinant, calculating the determinant probability, there is no parameter there. So we only have hyperparameters in the kernel. And then in this case, we can, again, just maximize the log determinant and then try to choose the best hyperparameters that maximize this log determinant. So the formula will be this one. That's the inference and the learning part. There are more things we can do with DPP. For example, we can consider like a conditional distribution of DPP. The case will be sometimes, say, when we want to make product recommendation, we don't want to make like general products to everyone. Rather, we want to make a more personalized product to each user. So when I compute the similarity between two items for recommendation, I will compute their similarity based on a specific user. So in this case, things become conditional. I will have some information X from my user, and then I will come up with a different gram matrix depends on X. And then use this gram matrix, I can set up my DPP and for the best subset selection. And a case study can be like this. So consider the multi-label classification problem. This can be like one application in the computer vision domain. Say I have an image, and then I want to ask, okay, what are the objects inside this image? In this case, my total set could be like many, many different objects, right? Like cars, dogs, cats, plane, desk, chairs, like everything. And then I want to pick out what are the possible objects in my image. So I can treat this as like a subset selection problem, selecting possible objects from my universal whole set. And then we can use a DPP model to model this. Together, we are going to introduce some like knowledge to make it better. For example, if we consider a desk and a chair, these two may be very likely to appear together inside one image, right? But if we consider the sun and the star, it's like very unlikely for sun and star to appear inside one picture, right? So besides just maximizing the regular DPP log determinant, we can also include this constraint terms such as cannot links and must links. So to describe what kind of items tend to be selected together and what kind of items are not tend to be selected together. So the final log likelihood we want to maximize is the regular DPP log determinant with two different constraints that we can come up with. So in this 2017 paper, they actually show using this model on the object classification inside images, achieve like a reasonably good result. All right, this finishes my all the things I want to discuss about Gaussian process and determinantal process, determinantal point process. These two things can be like a bit different from what we discussed before because they are distributions on functions and subsets. So yeah, I guess maybe at the first place, it's a bit to get the intuitive idea behind that. I think we had many good discussions to clear things up and help everyone here, including me, to get a better understanding of what these are. I can take some final questions if there are any.
Thank you, Shichang. So yeah, so I think the content indeed is like very inspiring. So I just want to make a comment to the ICML 2019 paper. It's 2019. I think the paper you mentioned that actually we do not really need to leverage any kind of pre-given graph structure, and we still can somehow define the kernel, right? And we have like this U, kind of try to use different ways to define the kernel. And then after that, then we can somehow leverage, kind of treat this kernel as some sort of this graph structure, and then we can have a very nice prediction on, I forgot the task, but I believe the performance is very good. So I think that gives us these insights. Okay, so in some cases, right, in some applications, I'm not saying all the applications, but some applications, actually the feature is dominant. So in this particular case, right, so whether we want to use some heuristic to construct a graph, or whether this sort of kernel, right, is the more fundamental way to capture the dependency between all those sites. I think that's something that was of thinking. A particular example, and also the example that given by Zijie last time, right, also show that in some cases we do not really need that structure, especially if the structure is secondary.
Yeah, I totally agree. So I guess this is related to what we have been discussing in our meeting. So sometimes the structure can cause sort of a noise, then maybe looking at the feature gives us a better understanding of the true underlying structure rather than the structure we observe. Any other questions or comments? Okay, if no, I guess maybe we can end up here. Thank you for bearing with me for 2 reading groups. I hope you all get something useful for you. Yeah, and I welcome any offline discussions with me regarding all the things I talked about.
Thank you, Shichang.
Thank
Thank
you.
you.